In the previous lecture, we saw that not all students that was randomized into the different treatment arms in the Project STAR stayed in the groups to which they were allocated. Some students left the different groups for various unknown reasons. However, as long as reallocation happens randomly, it does not invalidate the randomized control trial in terms of estimating the causal effect of the treatment. However, it's very likely that reallocation of individuals after randomization is not random. Students allocated to the control group may be unhappy by not receiving the treatment and might subsequently try to get into the treatment group anyway. In case of small classes, most students allocated to small classes are probably happy by being assigned to a small class and will not try to reallocate. But in many other cases, some of those allocated to treatment might subsequently try to defer treatment if possible. For instance, training or education for unemployed. Here it's often the case that many unemployed allocated to training or education does in fact not want to do this and tries to evade treatment. All this invalidates randomization and threatens the possibility to estimate the causal effect of a treatment from a randomized trial. Therefore, even if RCTs in theory enable researchers to estimate causal effects, in practice this may prove difficult. However, surprisingly, even in the case of non-random dropout, data from an RCT still enables the estimation of causal effects. The following slides explains how. Denote as before T the treatment indicator taking the value 1 if the individual is actually treated, that is, not only allocated to treatment but also actually treated, and 0 if not treated. Further, define Z equal to 1 if allocated to the treatment group and 0 or otherwise. C is the randomization indicator. Again, the observed outcome is outcome either as treated or untreated. Average outcome for those offered treatment is the average outcome without treatment for those offered treatment plus the treatment effect, the difference between outcome with and without treatment for those actually treated, obtained by multiplying with the treatment indicator for those allocated to treatment. Because allocation into treatment is randomized, the average baseline outcome for those allocated into treatment is equal to the baseline outcome for those not allocated into treatment. Now write the average gain if treated for those allocated to treatment C equal 1 separately for those who choose not to receive treatment T equals 0 and those who choose to receive treatment T equals 1. A fraction of those offered treatment declines and 1 minus this fraction accepts. The gains for those who decline treatment is 0 as they are not treated. The gain for those who accept treatment can be rewritten as a gain conditional on being offered treatment C equal 1 and accepting treatment T equals 1. We can now rewrite the average gain for those treated, both those accepting treatment and those declining, as a weighted average of the gain for those accepting and those declining treatment. Further, we assume that no one can enter treatment without being offered treatment. That is, we exclude the possibility that you can sneak into treatment without being offered treatment. Thus, we only allow for dropping treatment if offered. Hence, if you accept treatment, it must have been offered. That is, if T equal 1, this implies that C equal 1, but not necessarily the other way around. From this, it also follows that the average gain for those offered and accepting treatment is the same as the average gain for those who accept treatment, so we do only need to condition on that people accept treatment. From this, we are now able to derive the main result, the Bloom equation, named after its inventor, Howard Bloom. On the left-hand side of the equation, we have observed entities, that is, stuff that we can calculate from the observed data. And on the right hand, we have our object of interest, the average treatment effect for those treated. This implies that we can calculate the average treatment effect for those who accept treatment, even if some individuals selectively leave treatment. Now, given the algebra on the previous slide, we can now prove the Bloom equation. First, the average outcome for those offered treatment can be rewritten as the average baseline for those offered treatment plus the average gain for those who accept treatment conditional on being offered treatment. That is equal to the baseline outcome for those not offered treatment due to the RCT plus the gain for those offered and actually treated. This is again equal to the average baseline for those not offered treatment plus the weighted average gain for those offered and accepting treatment and those declining treatment. This is equal to the average baseline outcome for those not offered treatment plus the average gain for those offered and accepting treatment weighted with the fraction who accept treatment when actually offered treatment. Going back to the Bloom equation at the top of the slide, we can write the average outcome for those not offered treatment as the baseline outcome for those not offered treatment, as this group is not treated and they're thus unaffected by the treatment, but otherwise equal to those offered treatment. Collecting everything, we can write the nominator of the left-hand side of the Bloom equation as the baseline outcome for those not offered treatment, plus the weighted gain for those offered and accepting treatment, minus the average outcome for those not offered treatment. As can be seen, everything but the right-hand side of the Bloom equation nicely cancels out and leaving the right-hand side of the Bloom equation. This concludes the proof. So you've just seen that despite non-random dropout from an RCT, we can still estimate the causal effect of the treatment for those who accept treatment. Note that this is not the same as the average causal effect for those offered treatment, including those who reject treatment, and this has zero effect. We'll never know what happened to those who declined treatment, as this is not necessarily the same as what happened to those who accepted treatment due to selective dropout. We now turn to something different. When persons are selected into treatment, they are obviously aware that they are exposed to the treatment. This by itself may affect behavior. Therefore, while we can measure the causal effect of the treatment, the interpretation is less clear if people respond to merely being observed to a treatment. Do people change behavior because they are affected by the treatment or because they know they are being observed? This phenomenon is known as the Hawthorne effect, named so after the famous Hawthorne plant, where researchers tried to manipulate productivity by changing the work environment. However, it was later speculated that worker response was more due to being observed than to change in the work environment. Therefore, change in productivity was not a result of change in work environment, but from being observed by researchers. Therefore, research did not imply that change in work environment affects productivity, but that being observed affects productivity. Later, other researchers had doubted the so-called Hawthorne effect and concluded that the whole research design was flawed and that the data from the project does not allow either conclusion. However, to illustrate the idea behind the Hawthorne effect, we look at the star data. The table on the slide shows the class size by treatment arm, small classes, regular classes, and regular classes with a teacher's aide. From the table it can be seen that for classes of size 16 to 18 students, there are a number of classes of equal size in all three treatment arms. Thus, if the actual class size that matters and not treatment type, outcomes should be the same in all three treatment arms when actual class size is the same. If it's a Hawthorne effect, there should be a difference across treatment arms for the same class size. Some caution should be considered here though, because even if students are allocated into treatment by lottery, actually class size could be a result of selective attrition and dropout after the lottery. If we're willing to assume that ordinary classes that are observed to be small is a result of a negative selection, a bad teacher for example, and small classes that are in the high range for small classes is a result of positive selection, a good teacher, we should expect that the causal difference between class types is larger than the observed difference. Thus, the estimated difference between treatment arms for comparable class sizes is a lower bound for the true difference. With the above caveat in mind, the regressions on this slide shows the difference in math achievement in kindergarten for students in the different treatment arms. Students in small classes is the reference group. The regression results in the top panel shows results for classes in the range less than 29 students and larger than 12 students. And the bottom shows results for classes with less than 19 students and more than 16 students. This is a range from the table on the previous slide, where all treatment arms have classes of comparable size. From regression we find that the effect of the treatment arm is the same irrespective of whether we look at all class sizes or classes where class sizes are approximately the same across treatment arms. Therefore, with the caveat from the previous slide about the causal effect in the lower panel probably being larger than the estimated effect, we are inclined to conclude that the causal effect of being in a small class is more likely to be a Hawthorne effect rather than being an effect of being taught in a small class. Therefore, when teachers and our students are allocated into a small class in the STAR study, this induces them to teach or study harder, not because they're in a small class, but because they're expected to perform better from being in a small class. You should know, however, that this example is made up for the illustrative purposes of this course, and there's not a general agreement among researchers that the effect of the STAR project was indeed a Hawthorne effect. Until now, we have relied upon randomization to infer the causal effect from a treatment. The upside of this is that it is the design that allows the researcher to infer causality, and in principle, causality is undeniable. The downside is the external validity. Is the observed causal effect due to the mechanisms of the treatment, or is it a Hawthorne effect? If a randomized controlled trial is infeasible, or we want to rule out Hawthorne effects, there are alternative designs. One of the most notable is called the instrumental variable method. The basics of instrumental variables will be laid out in the following slides, and then the analogy to the estimator for the randomized control trial will be explained. Say we want to estimate the return to education by running regressions of log earnings on years of education. Then we would have learned that it would be dangerous to interpret the regression coefficient as a causal effect of years of education on log earnings unless we have either randomized years of education on individuals or that we have the full set of confounders that affect log earnings over and above years of education. So in the absence of data from an RCT on years of education, what to do? Imagine that we have available a third variable z that affects education but otherwise uncorrelated with earnings. Think of z as a variable that when it changes causes changes in the level of education but has no direct effect on earnings. One example could be an education reform that expands the minimum years of a compulsory school. It certainly affects years of education, but it's very unlikely that it affects individual earnings over and above education. Obviously, other things than school reform may affect education. This is indicated by the error term u. Also, other things than education might affect earnings. This is indicated by the error term e. It's also very likely that e and u are correlated, as they both capture the effect of stuff, for instance intelligence, that determines the level of education and earnings. We may write the figure as equations instead. One equation for the level of earnings, y, and one equation for the level of education, x. The instrumental variable only affects the level of education and not earnings. Hence, it should not appear in the equation for earnings. Note the resemblance to the treatment indicator C previously. In an RCT, C is the indicator of whether the subject was allocated to the treatment or control group, and T was the indicator of whether treatment was actually accepted. Here T is replaced by years of education X. However, the algebra is the same. Because we can estimate the causal effect on the treated using randomization into treatment, we can also estimate the causal effect of years of education C, e.g. the school reform, acts as a randomizer. In order for the instrument to deliver causal effects, we need it to be independent of everything else, just as randomization is independent of everything else in the case of the RCT. Therefore, given years of education X, the school reform Z must not have any direct effect of earnings Y. This in terms implies that Z must be uncorrelated with what otherwise affect both years of education as well as earnings. What follows does not seem to relate to how we derive the Bloom equation. We'll return to this in a couple of slides. Instead, we turn to how we derive the linear regression coefficient, now with the extension of the instrumental variable equation. We start by working with the covariance between the dependent variable and the instrument. Inserting the expression of the dependent variable in terms of x variable leads to what we can rewrite as the covariance between y and c as the effect of x on y, b times the covariance between x and c plus b times the covariance between e and z. This implies that we can write the fraction of the covariance between y and c and the covariance between x and c using the above expression of the covariance between y and c, and this gives us b plus a term involving b and the fraction between the covariance between e and z and the covariance between x and c. the denominator, the covariance between E and C, is 0 by assumption. Hence the fraction between the covariance between Y and C and the covariance between X and C is equal to B, the causal effect of X and Y. Therefore, the availability of an instrument allows us to estimate the causal effect of X and Y even when X and the error term E are correlated. As an example of the instrumental variables in the case of the return to education, we use the well-known case of quarter of birth, CE, for instance, Angrist and Kruger, 1995. The idea here is that due to the quarter of birth, there's a variation in when a person can leave compulsory school. All pupils start in compulsory school at the same date, but they might leave when they turn 15. As quarter of birth vary across respondents, but school start does not, quarter of birth affects the educational level of the respondents, as some pupils are allowed to leave compulsory school sooner than others. Using US panel data on birth cohorts from the 1930s, we find clear seasonal patterns in the mean years of education. Thus, quarter of birth, in part, affects your level of education. This is a graphical illustration of the covariance between the instrument C, quarter of birth, and the independent variable X, years of education. The next figure shows the covariance between log earnings and quarter of birth. Here we also find a clear seasonal pattern. Log earnings partly depends on your quarter of birth. If the instrumental variable assumption is correct, that the instrumental variable only affects the dependent variables through the independent variable, the reasons for quarterly changes in earnings is due to an indirect effect through education. Note that there is no empirical way of verifying the instrumental variable assumption. It remains an assumption. But if it's true, the ratio between the data in the two figures yields the causal effect of education on earnings. We can derive the instrumental variable estimator in an alternative way that may be a little more intuitive. In the first stage, we regress X, years of education, on the instrument, here quarter of birth. For simplicity, think of C as a binary dummy variable, taking the value 1 if the respondent is born in the first quarter and 0 otherwise. From this, we can obtain the predicted value of X given Z. The virtue of the predicted values of X using Z is that the predicted values of X only pertain the part of the variation in X that is common with C. Because C is independent from the error term U, by the IV assumption, the predicted values of X using C is also independent from U. In the second stage, we use the predicted values of X instead of the observed values of X. Note that the predicted values of X are also independent of the error term E, again by the IV assumption. Using the covariance operator, we can formally show what was verbally derived in the previous slide. Essentially, we're estimating the slope of X and Y using predicted rather than observed values of X. So the IV estimator is the covariance between Y and the predicted values of X divided by the variance of the predicted values of X. Replacing the predicted values of X by the expression in terms of the instrument C, we get the regression coefficient of Z on X, multiplied by the covariance between Y and C, divided by the variance of X. Plugging in the definition of the regression coefficient of C on Y, we finally get that the IV estimator, the covariance of Y and C divided by the covariance of X and C. Note that this is not a proof that the IV estimator consistently estimates B. It just shows that we get the IV estimator if we use the two-stage estimation procedure from the previous slides. However, we saw that the IV estimator was consistent on slide 10. We now conclude the derivations of the IV estimator by showing the analogy to the Bloom equation. Imagine that the instrument is binary, as in the example with quarter of birth, is either the first or the last 3 quarters. It can then be shown that the usual IV estimator, that is, the covariance between Y and C divided by the covariance between X and C, can be rewritten as the ratio between the difference between the expected values of Y across outcomes of the instrument and the difference between expected values of X across outcomes of the instrument. This is also known as the Wald estimator. If we replace the dependent variable X with actual treatment and the instrument as whether individuals are randomized to treatment or control, this is exactly the Bloom equation. So In the IV case, the IV can be thought of as replacing the lottery in the randomized control trial. Actually, what the IV does is that it replaces the randomization by design with randomization by nature. Somehow nature makes the randomization. To clarify the latter point, we show some examples on the next slide. Imbens and van der Klauw in 1995 studies the effect of having served in the Vietnam War on subsequent earnings. The idea is that having served in the Vietnam War may have reduced the earnings capacity of veterans due to lost labor market experience or on the ordinary labor market, or psychic disorder such as post-traumatic stress disorder due to combat experience. However, one can imagine that those serving in the Vietnam War are not comparable to those staying at home. Even though drafting to serve in the army was made by lottery, exemptions was possible, the former US President Bush being a notable example. Therefore, Imbens and van der Klauw use cohort indicators as instrumental variables. If one is willing to assume that there is no difference in earnings capacity across cohorts, being born in a different cohort yields lottery-like differences in drafting probabilities, independent of earnings. McKellen et al. 1995 studied the effect of heart attack surgery on health. However, people hospitalized for heart surgery may not be randomly selected. People with health insurance or people with knowledge of health problems may be more likely to be hospitalized than others. To generate lottery-like variation in hospitalization, McKellen et al. Uses proximity to cardiac health care facilities. For individuals with same background characteristics but different proximity have different opportunities for getting surgery in time. Evans and Rinkel 1999 studies the effect of maternal smoking on fetal birth weight. But it's very likely that women who smoke during pregnancy have different health profiles than women who do not smoke during pregnancy. Therefore, it would not be safe to assume that the entire average difference in birth weight across women who smoke and who do not smoke are the causal effect of smoking. To generate lottery-like variation in smoking, Evans and Rinkel use state cigarette taxes as the instrumental variable. As taxes vary across states, this is thought to generate differences in smoking habits across otherwise identical women. In this lecture, you have learned that even though there may be selective dropout from RCTs, one may still be able to estimate the causal effect of the treatment for those actually treated. Further, you have learned that it's possible to estimate causal effects in the absence of data from an RCT. What is needed is something else that generates lottery-like variation in the exposure of the dependent variable. If such variation is available, one can use the instrumental variable approach to estimate causal effects. In the next and final lecture, you'll learn even less restrictive methods that also may be able to yield causal estimates from non-randomized data.